Let's look at the very first question. In a steady flow of incompressible fluid, as the diameter is doubled, the velocity will be how much the velocity will become when the diameter is doubled. We have to find out. We have four options. It will be halved, doubled, and or increased four times or decreases four times. The main principle for solving this problem is by applying continuity equation. Let's look how to solve this problem. So for a steady flow of incompressible fluid, we can apply continuity equation. Okay, continuity equation can be applied for incompressible fluid flowing, having a steady flow. So uh, we know what is a continuity equation. I mean, the flow rate for discharge will be constant. That means A1 V1 equal to A2 V2. Okay, so A1 and V1 are the corresponding area and velocity at one part or one inlet, and A2 and V2 are the another condition. So same way we can solve this problem. First condition is a very normal one, but second they have mentioned the diameter is double, right? So I'll be applying like A2 will be, since it's the it will be circular form. Obviously it will be pipe. So will be for a circular pipe it will be pi d square by 4, applying the area of circle, substituting 2d1 at the diameter part, will be getting like 4 times the first area. So the relation between area will be A2 equal to 4A1. Okay, the will be the second area when the velocity is sorry, that when the diameter become double, area become 4 times of the first one. So just applying this on the continuity equation, we will get the answer will be V2 is equal to V1 by 4. So the velocity decreases by a factor of 4. 1 by 4th of the initial velocity means this decreasing by a factor of 4 when the diameter is doubled. So second question, in a fully developed turbulent flow, the diameter is half without changing the flow rate. The frictional drop will change by what factor? So it is a turbulent flow and diameter is halved and flow rate is kept constant. And both the condition the flow rate is kept constant. You have to find the relation of frictional drop. How much is this factor changing after the this condition? So how to do this one? So since this question has a frictional factor, this is solved by applying Darcy-Weisbach equation and continuity equation. We'll be using Darcy-Weisbach equation and continuity equation for solving this one. So the general equation or general formula of Darcy-Weisbach is FL V square by D into 2G, where F is a Darcy frictional factor and L is the length of the pipe or whatever cross section is considering. D is the pipe diameter. D is the pipe diameter, V is the flow velocity, and G is the gravitational acceleration or acceleration due to gravity. So in question we have two conditions. So that is, I will show you. Okay, this is two condition given. The flow rate is kept constant. Okay, whenever flow rate is mentioned, we have to apply continuity equation for solving that problem. We have to keep in mind that when flow rate is mentioned, we can use continuity equation because A1 V1 equal to A2 V2. So that's the first point they have told, the flow rate is kept constant. Also the area, sorry, the diameter is halved. So this is the initial equation. Since it is an circular cross section, obviously you can use the area of circular cross section, that is pi d square by 4. So the diameter is half. So new area will be one by fourth, or it will decrease the 4 times the initial one. Okay, and our equation, Darcy-Weisbach equation, has velocity term, area term. So all we have to doing is we are finding the new term or relation of velocity and acceleration to substitute the Darcy-Weisbach equation to find the frictional factor relation. So by applying to the continuity equation, that is A1 V1 equal to A2 V2, they have written as AB is equal to A dash V dash, both are same. So from that, applying this diameter or this new area relation, the new velocity will be 4 times the initial velocity. So new area is 1 by 4, so decreased to 4 times initial one, and the new area 4 times increases or multiplied the initial one. So we got the relation of area and velocity, all I have to do is substitute in the Darcy-Weisbach equation. So substituting the main equation, that is Darcy-Weisbach equation, we'll be getting a new frictional factor will be 32 times the uh, older one. Okay, initial condition. So it will become 32 times the uh, previous frictional factor. So that's the relation of frictional factor by this given condition. The velocity profile in the turbulent flow is what nature? We know there are velocity profile for different types of laminar, turbulent. Okay, so the corresponding velocity profile will indicate some definite structure or nature. So we have to find which one. We have linear, logarithmic, second degree polynomial, and parabolic. So among these, which one is having the velocity profile? So the answer is the velocity profile of turbulent is logarithmic. Okay. Parabolic is of laminar and linear and secondary is also not possible. Velocity profile in the turbulent flow is logarithmic. It will be look something like this because this is the nature of nature profile, velocity profile of turbulent flow. Condition for maximum power developed during viscous flow through a closed conduit. So this closed conduit can be anything. It could be a pipe or it could be a nozzle. Anyway, you have to find the maximum power condition considering the frictional factor. Okay, so how do you get the maximum uh, power? Which relation satisfies this condition? So the solution for this problem is very much bigger, but it is a generalized solution or fact. That's the maximum power condition. So I will explain some of the terms related to how we get the final answer. So these are the basic assumption or steps taken for solve this problem, that the head available at the end of the pipe or nozzle or any closed conduit will be head at the inlet minus head loss the friction. Okay, this is the head at the inlet. That means the total head that can be available for the flow. But even though when the fluid flows through even pipes or whatever medium, there will be some loss due to friction. Okay, so we won't get the actual head. There will be some loss. The remaining head is of the formula HF minus HF. And HF is a loss of air due to friction in the pipe HF. And it is given by Darcy-Weisbach equation, that is 4 FL V square by D into 2G, or you can either write the FL V square by G into 2G into D. Both are same for Darcy-Weisbach equation. And there's a lot of steps. So this is general equation for the power transmission. Okay, power transmission equation. Okay, this is a general equation for power transmission, and the final equation will be like this: half rho AV cube by 1000. And the maximum condition for maximum power transmission through the nozzle will be, this is a maximum condition. This is a non-fact. Okay, it's better to learn this relation rather than trying to solve it. So this is like a relation. HF will be the head loss due to friction will be 1 by 3 of the actual head to get maximum power transmission. This should be the condition. Okay.